Okay, so welcome everyone. I want to give a short talk showing how you can study OpenMP applications with the help of the Vampir performance analysis tool. And I will present you some case studies in this talk showing typical performance problems and how you can detect it using Vampir. And let me start by this sparse matrix vector multiplication example where we will see some load imbalances. So yeah, it's pretty simple in this case. So it's a matrix multiplication with sparse populated matrices. So only the non-zero elements are stored in order to save some memory. And as you can see here in the algorithm, also computation is only executed for non-zero elements in a row. So you can transform this simple algorithm directly into a naive OpenMP program. And you see there's one problem with these parallel loop. So the rows of A will be evenly distributed across all threads. And as you can see, there might be some non-zero elements. This may influence your load imbalance. So if you program your application like this and you monitor your application with Vampir and try to analyze the performance, and you have a look on the resulting trace file, you will see a picture like this. And what you see directly on the first sketch here is that this blue color is dominating. What is this blue color? So as you can see in the function legend, each individual function group has its own color, and blue stands, for example, here for OpenMP synchronization. So especially you can imagine it as waiting time. And waiting time is not a good thing for performance program. So what's the problem here? So you have a lot of processes which do not compute very well because they have a lot of these non-zero zero elements, and you have the master thread with a lot of rows with non-zero elements. So the load imbalance is really visible in this sketch here. So what can we do here to improve the performance of this program? So in this case, it's simply easy. So we can try to use the schedule pragma of OpenMP and switch from static scheduling to the dynamic scheduling. So this will achieve a better load distributions across all threads. And if you manipulate the source code of your program in this way, compile the application again, run it again, and create performance data out of it, and use the Vampir tool, you immediately see this looks much better, because now almost 90% of your program is time is spent in the OpenMP loop, so it's doing any sort of computation, and the amount of synchronization was dramatically reduced. So here we see these two pictures, the unoptimized version, the optimized version one, but Vampir provides a nice feature which is very helpful for this performance comparison. It's called the comparison view, where you can see both versions of the program side by side, and you directly see the improvements in runtime of the application. So the runtime is decreased by nearly a factor of 2 just by switching from static scheduling to dynamic scheduling. And as I already told, so you see this dramatical decrease in the share of synchronization primitives. So this was a basic example showing a typical problem of load balancing within OpenMP parallel loops. But sometimes it's not that easy. So often you use a combination of multiple parallel paradigms. For example, you do not use only OpenMP, you use it in combination with MPI. And then you have a problem that your load imbalances within the OpenMP parallel loops. You can see it here. You have, again, these blue areas indicating waiting time in OpenMP loop. But the problem here is that this load imbalance in the OpenMP load propagates in your program execution and causes, in addition, MPI waiting times, because after the parallel loop here, there is some MPI communication. In this case, it's a wait all, and so this results in one MPI process coming late in this collective operation, and all the other participants have to wait until this last process arrives in the collective operation. So it's not only OpenMP you have to be care of, so you also should care about all parallelization paradigms you use, and Vampir provides you a tool that can show you all these effects in a single view, so you can investigate all your problems with only one tool in hand. So the third case study, Trinity, it's an RNA sequencer assembler, is a production code, and in this case study there was a scaling study executed. So they tested how well these applications scales with multiple OpenMP threads. So they done experiments without OpenMP, so the sequential version, with 2 OpenMP threads, 4, 8, and 16 OpenMP threads. And as you can see, as you increase the OpenMP number of threads, your waiting time increases. So also here marked in these blue colors. So it's really visible here that this application does not scale well. So what is the problem with this program? So is it maybe, as we saw in the first example, a misuse of OpenMP pragmas? In this case, it was not the OpenMP pragma which causes some problems, or the OpenMP scheduling. It was the workload within the OpenMP parallel loop. So you see these function string streams, and this uses C++ objects. So within these functions, new string stream objects were created. And this creation was guarded by mutexes, and these mutexes caused a serialization of your work execution. So this problem was solved by moving the creation of these string streams out of the loop and doing only computation within the loop, and thereby they were able to achieve a better scaling, so they could speed up the execution from 2.3 to 8.9, and you see the amount of waiting time could be dramatically decreased. And also these scaling studies are well supported by the Vampir tool suite because of these visual comparison of multiple executions, and you directly see how the application performs in the different setups of your experiments. So the last case study I want to show you here is the LSMs code, and here we want to see how we can use OpenMP to utilize efficiently hardware resources. So it's not about parallelizing your workload, it's more that you have, in this case, a node with 20 cores, and you had multiple, in this case, 4 GPUs, and you want to try to create enough workload to utilize all the GPU resources. And in this use case, several setups were executed, and you can see usually you would expect, for example, that a one-to-one mapping fits fine, so each thread, for example, uses 1 GPU. But in this experiment, it reveals that the setup with using 20 CPU cores was the fastest, and want to utilize all the 16 GPU core efficiently. Yeah, so that was all the case studies I want to show you. I hope you enjoyed the talk, and thank you for your attention.